So in Bode plot, we are doing the frequency response analysis, right? So the input is a sinusoidal input. So we are going to give a sinusoidal input and see what will be the response. So in steady state, the sinusoidal input to a linear system, it generates sinusoidal response of the same frequency, but they differ in the amplitude and phase angle from the input. And then the Bode plot, then what are the advantages of using the Bode diagram or the Bode plot? So in this case, the multiplication of magnitude, it can be converted into addition. So we have a simple method, that is the approximate log magnitude curve is available. It is also known as asymptotic approximation. We don't require to plot the exact magnitude plot. We can approximate using the asymptote. So such approximation by straight line asymptote is sufficient if only the rough information on the frequency response is needed. So this Bode diagram, it consists of two graphs. First one is the magnitude plot. Okay, so one is a plot of the logarithm of the magnitude of a sinusoidal transfer function, and the second one is the phase angle. So both these magnitude and phase angle plot are plotted against the frequency on a logarithmic scale. So this Bode plot, it will be done on a semi-log graph paper. Then we discuss these basic factors of our transfer function, right? The gain, the pole or zero at the origin, or we can say integral of derivative factor. Similarly, the first order factor, it may be on the numerator, on the denominator. Similarly, the last one is the quadratic factor. So we discuss that what will be the this shape of the curve for this log magnitude curve for this constant gain k. So this will be a horizontal straight line at the magnitude of 20 log k. And the phase angle of gain k will be 0. Right? We have discussed all these things. And similarly, let's consider this pole 0 at the origin. So our transfer function is g of s equal to s. That means the 0, only one 0 at the origin. So its magnitude will be this 20 log of omega. So by varying the value of omega from this 0.1 to 1, we can see when the value of omega equal to 0.1, we are getting the magnitude minus 20 dB. Similarly, when omega equal to 1, we are getting the magnitude to be 0 dB. So we can say in one decade, there is a change in plus 20 dB. So for a pole, we can say the slope of the magnitude curve will be 20, sorry, for a 0, right, for a 0, the slope of the magnitude curve will be 20 dB per decade, or we can say 6 dB per octave, okay, 6 dB per octave. Similarly, we know the phase angle. The phase angle will be tan inverse of this complex, this imaginary part by the real part. So in this case, the real part is 0. It will be only tan inverse of omega by 0. So we are getting 90 degree. So now this will be the slope, right? 20 dB per decade. At 0.1 frequency, we have this magnitude minus 20, and at frequency 1, we have the magnitude 0. So this will be the slope, right? This will be the slope, which is 20 dB per decade. Similarly, for a pole, the slope will be minus 20 dB per decade. So remember, so for pole, the slope will be minus 20 dB per decade, and for 0, the slope will be plus 20 dB per decade. So all these things we have discussed in last class. So this is only the definition, the minimum phase and non-minimum phase system. The transfer functions having neither poles or zeros at the right half of the S-plane are known as minimum phase transfer function. Okay, if in the right hand side there are no pole or zero, that will be in a minimum phase system or minimum phase transfer function. And similarly, the transfer function having poles and or zeros in the right half of the S plane are known as non-minimum phase system, or we can say non-minimum phase transfer function. Okay. So if there is no polar zero in the right hand side, then it will be a minimum phase system. And if any polar zero is in the right half of the S plane, then it will be a non-minimum phase transfer function. So let's come to this important part regarding this Bode plot. So how can we check the stability from our Bode plot? So for that we have to define these four terms. Okay. So first one is the phase crossover frequency. So it is normally denoted as omega p or omega pc, right, for phase crossover frequency. So this omega pc, it is the frequency at which the phase angle of the open loop transfer function equals to minus 180 degree. Okay. The phase crossover frequency is that the frequency at which the phase angle of the open loop transfer function is minus 180 degree. Remember, the next term is the gain crossover frequency. So it is the frequency at which the magnitude of the open loop transfer function is 1 or unity. Okay. The phase crossover frequency, the frequency at which the phase angle of the open loop transfer function is minus 180. And for gain crossover frequency, the frequency at which the magnitude of the open loop transfer function is unity. Similarly, the gain margin is denoted Kg. So it is the reciprocal of the magnitude of G of J omega at the phase crossover frequency. So mathematically, we can say this gain margin is that it is the reciprocal of magnitude of G of J omega at the phase crossover frequency. That is, this Kg is equal to is 1 by this magnitude of G of J omega 1. And this J omega 1 is the omega 1 is the phase crossover frequency here. Okay. We have to put the phase crossover frequency here. So similarly, we can write in dB, this kg dB will be equal to 20 log of kg. So we can write, if we make it 20 log, then it will be minus 20 log g of j omega 1. But this omega 1 is the phase crossover frequency. Or we can analytically define this gain margin as it is the additional gain required to make the system into the to bring the system to the verge of instability. That means this much amount of gain, if we add to our system, then our system will become unstable. Okay. So mathematically, you can derive like this one. This kg equal to 1 by this magnitude of g of j omega pc. But this definition, it is the amount of additional gain at phase crossover frequency required to bring the system to the verge of instability. Similarly, phase margin also we can define like that. It is the amount of additional phase lag at the gain crossover frequency required to bring the system to the verge of instability. Right, margin means we can say the margin means we have some point left. Okay, so that margin we have to define the gain margin. So gain margin means this amount of gain we require to add into the system so that it will become unstable. Similarly, phase margin, it is that amount of additional phase lag at the gain crossover frequency that will make our system unstable. Okay, clear? This definition, phase margin, gain margin, and the phase crossover frequency and gain crossover frequency. So remember that when calculating this gain margin will be calculated at the phase crossover frequency, and the phase margin will be calculated at the gain crossover frequency. Both will be vice versa. Okay. The gain margin will not be calculated at the gain crossover frequency. The gain margin will be calculated at the phase crossover frequency, and the phase margin will be calculated at the gain crossover frequency. So in diagram, we can check this phase margin, gain margin, the phase crossover frequency and gain crossover frequency. So here in this Bode plot, we have to draw both the phase plot and the magnitude plot in a single graph. Okay, we have to draw in a single graph this gain plot, this phase plot and the magnitude plot. So let's suppose this is our magnitude plot and this is our phase plot. According to definition, this will be the gain crossover frequency. So this is our gain crossover frequency. So from this diagram we can say the frequency at which the magnitude plot is intersecting the 0 dB axis, right? From this diagram we can say the frequency at which our magnitude plot is intersecting the 0 dB axis, that frequency is known as gain crossover frequency. But here in the definition it is written the frequency at which the magnitude of the open loop transfer function is unity. But here it is intersecting at the 0 dB axis. Can anyone say why? What is the difference? The magnitude of this open loop transfer function should be 1 at that frequency. But in this diagram we can see that at gain crossover frequency the magnitude plot is intersecting the 0 dB axis. Can anyone say why and what is the difference? You can spot.
A log scale.
Yes, it is a log scale, right? So 20 log 1 will be 0. So that is why it is intersecting the 0 dB axis. Similarly, the phase crossover frequency will be the frequency at which this phase plot is intersecting the minus 180 degree line. Clear? Or we can say the phase angle of this open loop transfer function is minus 180 degree. So at that frequency it is known as phase crossover frequency. Clear? From this diagram the phase crossover frequency and gain crossover frequency. Next is we have to identify the gain margin and the phase margin. So you know this gain margin is calculated at phase crossover frequency. So this is our phase crossover frequency. So we have to draw a line up to this. So now we can see this point, right? This point is the gain margin. So this will be our positive gain margin because this is the amount of additional gain we require to add in the gain so that our system will become unstable, right? So from this 0 to negative to going out towards 0, so we are adding the gain margin. So this is a positive gain margin. And similarly the phase margin is calculated at gain crossover frequency. This is our gain crossover frequency. So we have to draw this line up to this minus 180 degree line. Okay. So now this will be the phase lag, the additional phase lag, right? Because this phase margin is, by definition, it is the amount of additional phase lag that is required to bring the system to the verge of instability. So this is the amount of additional phase lag that we are adding to our system. So this will be our positive phase margin. This will be a positive phase margin. So similarly, in this case, we can see so this will be a negative phase margin, right? Because we have to subtract this gain margin so that we will get this 0 dB, or we can say that it will be unstable. So this will be a negative phase margin. Similarly, in this case, it will be a negative phase margin. So negative gain margin, negative phase margin. So how we can say that this is a positive phase margin or negative gain margin? So if the phase crossover frequency is greater than the gain crossover frequency, at that time we will get this positive gain margin and positive phase margin. Clear? Because the frequency will start from here, this side, will go on increasing from this side. So this gain crossover frequency is smaller than the phase crossover frequency. So we can say at that time we will get positive gain margin and positive phase margin. But in this case we can see the phase crossover frequency is less than the gain crossover frequency. So we will get negative gain margin and negative phase margin. So if both the gain margin and phase margin are positive, our system will be stable. And if both are negative or any one of this is negative, either the gain margin or phase margin is negative, then we will get unstable system. So by simply if we say to check the stability without calculating the GM and PM, right, the gain margin and phase margin, if the phase crossover frequency is greater than the gain crossover frequency, our system will be stable. Clear? Because at that time both this GM and PM will be positive. So if the phase crossover frequency is greater than the gain crossover frequency, at that time we will get a stable system. And if this omega PC is less than this omega GC, then we will have unstable system. So either any one of this gain margin or phase margin is negative, then our system will be unstable. So we'll see in examples. So yesterday we discussed the initial slopes, how we can determine the initial slope for type 0, type 1 and type 2 system. So you have to remember this one so that you can easily get for this type 0, type 1, type 2 or type 3 system the initial slope of the magnitude plot. We have discussed this for type 0 system. The initial slope will be this one, 20 log k. The starting point will be 20 log k and the initial slope will be 0 dB per decade, right, for type 0 system. Remember this one, for type 0 system, the initial slope will be 0 dB per decade and the starting point will be calculated by this formula, 20 log k. K is the system gain. Similarly for type 1 system, we have to locate omega equal to k on 0 dB axis first. Okay. For type 1 system, we have to locate omega equal to k on 0 dB axis, and at this point we have to draw a line of minus 20 dB per decade. Right, we have to draw a minus 20 dB per decade till it intersects the y-axis. So that intersection will be the starting point of our magnitude plot. Similarly for type 2, this will be implemented. So type 2 system, we have to mark this omega equal to root over of k on the 0 dB axis for type 2 system. Okay, we have to locate this omega equal to root over of k on 0 dB axis and then draw a line of minus 40 dB per decade until it intersects the y-axis. The intersection point will be the starting point of our magnitude plot. So similarly, so what will be for type 3 system? What will be the initial slope and the intersection point?
Cube root of k?
Yes, omega, we have to mark omega equal to cube root of 3 and we have to draw a slope of, what will be the initial slope?
Minus 60.
Minus 60 dB per decade.
सर 0 dB एक्सिस कोटा है.
अच्छा, okay, no problem. So first, while drawing this Fourier plot, we have to make two plot in a single graph. Two plot in a single graph. Okay, first one is the magnitude and then second one is the phase angle plot, or we can say phase plot. So let's say this is our this similar graph paper. Okay, so we have to plot two graph. This one is magnitude, this one is for magnitude plot, and this one is for phase plot. So this will be minus 20 minus 20 20. So this is for this phase plot and this is the magnitude plot. Okay, so this will be this 0 dB axis because it is in dB, right? The magnitude is in dB and this phase angle is in degree. This phase angle is degree and the magnitude is taken in dB. So this is our 0 dB axis. This is our 0 dB axis. Okay. Similarly, in phase angle, our reference will be minus 180. The reference will be minus 180. So similarly, it will be minus 160 or 140 according to our scale. Similarly, it will be 140 minus 140. Similarly, it will be minus 200. It will be minus 240. Right. So this is our 0 dB axis for the magnitude plot. So this will be minus 20 dB. This will be minus 40 dB. This will be 20 dB and this will be 40 dB. Clear? We have to draw two segments. One is the for a magnitude plot, another is for this phase plot. So for phase plot, the reference line is minus 180 degree, and for magnitude plot, our reference line is 0 dB. So suppose our magnitude plot is like this one, okay, and similarly we are getting the phase plot to be like this one. So we can see this is our magnitude plot. So this is the frequency in our this okay. So in the x-axis we have to take the frequency. Okay, x-axis, this is our y-axis. So in x-axis we have to take the frequency. So we cannot take the starting point 0, the starting frequency 0, right? Because why? Because this 20 log of 0 will be minus infinite. So you can take as per your requirement. So let's start with 0.1. Initial frequency is this point is 0.1. Similarly, this will be 1. This will be 10. This will be 100. This will be right, because in our x-axis this is a logarithmic scale, but y-axis it is a linear scale. That is why it is known as semi-log graph paper. It is a semi-logarithmic graph paper. So this is 1 decade from 0.1 to 1 frequency, 1 decade, similarly 1 to 10, 1 decade, 10 to 100, 1 decade. So you can write this as omega in x-axis omega or log of omega. Okay, log of omega, because log of omega means log of omega is the log of 1 is 0. It will be 1, right? If you take the log scale, it will be 0, 1, 2, and this will be 3. So to know, we just simply take omega, okay, frequency, because we have to identify the frequency. You can write log omega also, because log of this term will be this one, 0, 1, 2, 3. Okay. So here we can see the magnitude plot is intersecting this 0 dB axis, right? This one, this 0 dB axis at this point. So this will be our gain crossover frequency, omega GC. So we can see the omega GC will be around 50 radian per second, right? Because 10 to 100 means it will be around 50. So we can see the gain crossover frequency is 50 radian per second. Similarly, the phase crossover frequency, so the phase plot intersected the minus 180 degree line. Okay, so this one, so this frequency is our omega PC, the phase crossover frequency. So this will be around 300 radian per second. Okay, I am not taking exactly, so it will be around this 300 radian per second, the phase crossover frequency. Because 100, 200, 300, we have to go up to 1000. So it will be around 300 radian per second. Similarly, the omega GC is 50 radian per second. So we can say at the frequency of 50 radian per second, the magnitude plot is intersecting the 0 dB axis. So this is our 0 dB axis of the 0 dB line. Similarly, at 300 radian per second, this phase plot is intersecting the minus 180 degree line. So this will be our phase crossover frequency. So to determine the gain margin and phase margin, we have to draw the lines from this omega PC and omega GC. So we have already drawn a line from omega GC. Then we have to draw a line from this one, this omega PC up to this 0 dB axis. So now this much, it will be our gain margin. Right? Because if we add this much of gain, then our system will be at this 0 dB line. So at that time, it will be marginally stable. Okay. So at this point, our system is marginally stable. So beyond that, it will be unstable. Right? Beyond the marginal stability, our system will be unstable. So if we add this much of gain, so let's say in this diagram, we can say we have to add a 40 dB, right? If we add 40 dB, then we will get this 0 dB. So we can say this is a positive gain margin. Similarly, in this case, this will be the phase margin for this gain crossover frequency from this minus 180 to this one, because this phase margin will be calculated at this gain crossover frequency. So from this gain crossover frequency, we have to draw a line up to this minus 180 degree axis. So this much will be the phase margin. So this is our phase margin. So according to definition, the phase margin is the amount of additional phase lag. Okay, not additional phase. It is the amount of additional phase lag that is required to make our system unstable. So that means we have to add this much of phase lag. So if this is 120, then suppose this line is 120 degree, then our phase margin will be, this one will be positive phase margin. The value of phase margin will be 120 to 180, it will be 60 degree. Where the gain margin is here 40 dB. Here phase margin, gain crossover frequency, phase crossover frequency. So the initial slopes we have discussed. So we have done two.
Sir, the magnitude of phase angle ta jette positive hobo sette unstable hobo system.
ना जदि आमर फेज मार्जिन फेज मार्जिन केन मार्जिन कोटा कहउछ
सर फेज और मैग्नीट्यूड दीटा जरा कहउछ
ना जोटा जत्ते पॉजिटिव हबो सेते सिस्टम टा स्टेबल हबो तर पॉजिटिव सिस्टम स्टेबल होआ पई गेन मार्जिन और फेज मार्जिन हमर पॉजिटिव हेबा दर तो जत्ते अधिक हो सेते भल ना तो मने कर सपोज हला तमे उटे पहाड़ बुलिया पई जाइछो आ गोटे क्लिप अच्छी सेटा हला क्लिपटा हला एटा से क्लिपटा हला तो तमे जते दूर रहिछ से क्लिप रु सेते तमे स्टेबल अछ ना जते पाकु जीवो तमर क्लिप रु पडिया चांस अधिका हबो तो जते अधिका तमे पॉजिटिव हबो सेते अधिका तमर से क्लिप रु पडिया चांस कम हबो तो सेही टर्म्स रे जते अधिका हमर पॉजिटिव हो गेन मार्जिन सेते हमर सिस्टम अनस्टेबल हबार चांसेस कमी जीवो सिमिलरली फेज मार्जिन भी जते पॉजिटिव होबो सेते हमर सिस्टम स्टेबिलिटी अधिक रहिबो So we have discussed these two examples. So this is for type 0 system, right? a type 0 system. So what will be the initial slope? Anyone? We have already discussed this example. What will be the initial slope? କୁହ ଛୁଆଟା କୁହ କିଛି ତ କୁହ। ତାହେଲେ କିଛି ବୁଝିନ କାର୍ଡ ମଡେଲ ସବୁ ଦରକାର ହବ ହେଲା ବୋର୍ଡେ ପ୍ଲଟ କମ୍ପେନସେଟର ଡିଜାଇନରେ ରୁଟ୍ ଲୋକ ସବୁ ବୋର୍ଡେ ପ୍ଲଟ କ'ଣ କେହି କିଛି କହିବନି। This is a type 0 system. So what will be the starting point of our magnitude plot?
0 degree, 0 degree per decade.
0 degree per decade कौन starting point ना slope
Slope
60 degree per decade.
60 degree per decade तुम्हारे कुह किसी नहीं डरियार नहीं कुह तुम यदि मत डर आंसर देवाई तो बाकी टीचर मैंने तुम किसी कहून ऊँचू कहून so we know for type 0 system the initial slope will be is 0 dB per decade and the starting point can be calculated by this formula, right? 20 log base 10 of k. So k is 1000. So our starting point will be 60 dB on the y axis and similarly the initial slope will be 0 dB per decade. Then the next step is to identify the corner frequencies. So we have two poles, so we will have two corner frequencies. So omega 1 will be for this one 1 by the time constant, so 1 by 0.1, so it will be 10 radian per second, and the second corner frequency is omega 2 is for this one 1 by 0.001, which will be equal to 1000 radian per second. So we have two corner frequencies. Okay. The corner frequency, we can define the corner frequency is the frequency at which two asymptotes break. Okay, we can define like that the corner frequency. Okay, so I will draw this. Try to draw. So let's start from frequency 1. Okay, 1, 10, 100 and 1000. Okay. So first we already know our starting point of our magnitude plot. The starting point is this one 60 dB. Right. The starting point is 60 dB. So the initial slope will be 0 dB per decade. Excuse me for my straight line drawing. Okay. It will be 0 dB per decade. So next step is to we have to identify the corner frequency. So we have two corner frequency. One is at 10 and another is at 1000. These are our two corner frequencies, right? Two corner frequency 10 and 1000. And the initial slope is 0 dB per decade because it is a type 0 system. And the starting point is determined by this 20 log of k. So this is our initial slope of our magnitude plot. So this slope will continue up to the first corner frequency. So the first corner frequency is this one, right? Here first corner frequency. So this slope will continue up to first corner frequency. So we don't have to draw this line. Okay. So this will continue up to the first corner frequency. So then the next corner frequency is 10. So now this 10 is the frequency 10 is from the pole, is from a pole. So now the next slope will be the starting it was 0 dB per decade, and then there is another pole. So we have to add this minus 20 dB to this initial slope. So our slope will be like this one now, this minus 20 dB per decade. So just let me see the graph. So we have to add a slope of minus 20 dB up to the next corner frequency. It may not intersect this point, okay, this corner frequency. I will tell you how we can do, how to draw this minus 20 or minus 40, this slopes. So and then from this corner frequency, we have to draw a minus 20 dB per decade slope. Minus 20 dB per decade, okay, up to the next corner frequency. So we have to see the next corner frequency is 1000. So this 1000 corner frequency is also from a pole, right? So single pole means another minus 20 dB per decade slope. So now it is minus 40. So our final slope will be like this one, this minus will be this minus 40 dB slope. Minus 40 dB per decade slope. Similarly, this is minus 20 dB per decade slope, and this is this 0 dB per decade slope. Here the magnitude plot in the draw habo.
ସେ ପୁରା ଡାଇରେକ୍ଟଲି ଜିରୋକୁ କେମିତି ନେଇ ଆସିଲେ ସେକେଣ୍ଡଟା?
କୋଉଟା ଏଇଟା
ଆଜ୍ଞା
ଏଇଟା କିଛି ନାହିଁ ହେଲା, ଦେଖ ଫାଷ୍ଟ 0 କୁ ଆଣିବା କିଛି ମାନେ ନାହିଁ ହେଲା, ଆମକୁ ଡ୍ର କରିବାର ଅଛି ଅପ୍ ଟୁ ଦ ନେକ୍ସଟ କର୍ନର ଫ୍ରିକ୍ୱେନ୍ସି। ତ ଏଇଟା ତମେ ଡ୍ର କରି ଏଠି ହିଁ ଆସିବ, ବଟ୍ ଇଟ୍ ମେ ବି ଲାଇକ୍ ଦିସ୍ ଅଲସୋ, ଓକେ, ଏମିତି ବି ଆସିପାରିବ। ତ ଦ୍ୟାଟ୍ ମିନ୍ସ ଏଇ ପଏଣ୍ଟ ଯାଏଁ ଆମକୁ ଡ୍ର କରିବାର ଅଛି, ବିକଜ ଏଇଟା ହେଲା ନେକ୍ସଟ କର୍ନର ଫ୍ରିକ୍ୱେନ୍ସି 1000। ଏ ଲାଇନଟା ତଳକୁ ବି ଆସିପାରିବ ହେଲା। ତ ଏଇ ପଏଣ୍ଟ ଯାଏଁ ଆମକୁ ଡ୍ର କରିବାର ଅଛି ଅପ୍ ଟୁ ଦ ନେକ୍ସଟ କର୍ନର ଫ୍ରିକ୍ୱେନ୍ସି। ଏଇ କର୍ନର ଫ୍ରିକ୍ୱେନ୍ସିରୁ ତାପରେ ଆଉ ଗୋଟେ ପୋଲ୍ ଅଛି ଏଇ 1000 ଫ୍ରିକ୍ୱେନ୍ସି ପାଇଁ, ସୋ ଆଉ ଗୋଟେ ଏଡ୍ ହବ, ଏଇଟା ହବ ଯୋଉଟା ହବ ଆମର ମାଇନସ୍ 40 dB ସ୍ଲୋପ୍। ଏଇଟା ତଳକୁ ବି ଆସିପାରେ, ଉପରେ ବି ରହିପାରେ ହେଲା, ଏମିତି କିଛି ମାନେ ନାହିଁ ଯେ ଇଣ୍ଟରସେକ୍ଟ କରିବ ବୋଲି। ଯଦି ତମେ ଏକ୍ଜାକ୍ଟଲି ଡ୍ର କରିବା ତାହେଲେ ଏଇଟା ଏଇ 1000ରେ ଇଣ୍ଟରସେକ୍ଟ କରିବ। Intersect at this point. Okay. Now our doubt is magnitude plot re. Okay, very good then. Then I am going to do phase plot. Okay. Again, I am going to system stability check kariya achi. So without both this magnitude and phase plot, we cannot comment on the stability of our system. For phase plot, we have to write the diagram. So we in this transfer function we have only poles, right? We have only poles, no zero or not even a pole at the origin. So what will be this equation of this angle? So it will be this minus tan inverse, minus tan inverse of this one, right? This 0 point, you know, the imaginary part by real part, right? So imaginary part is 0.1 omega divided by 1. So you can just simply write this 0.1 omega divided by 1. So we can neglect the 1. And we have another pole, so we have to add another minus this tan inverse 0.001 omega. That is the pole, right? 0.001 omega, because we have to vary the frequency omega. So this will be our this phase angle. So we can see here we have taken our this frequency from 1 to
minus tan inverse कहीं नहीं आला denominator रे अच्छी बिल्ली।
हाँ डिनोमिनेटर थिले माइनस हबो न्यूमरेटर थिले प्लस हबो
ओके सर
क्या जदि आम या लिखा इक्वेशन रे सिंपली भी लिखिया डिवीजन रे कोन हबो k रो कोन हबो tan इनवर्स ऑफ दिस 0 by k और तले हबो tan इनवर्स ऑफ दिस 0.1 ओमेगा प्लस tan इनवर्स ऑफ 0.001 ओमेगा जदि ऊपर को नहीं आसीबा ताले कोन दिटा माइनस हे जीवो या डिवीजन अछि
यस सर
then we can see we are varying our frequency from 1 to 1000 हला तो तुम पार कैलकुलेटर समस्त पाखरे साइंटिफिक कैलकुलेटर अछि तो आई यूजिंग अछि तमर फंक्शन अछि टेबल कैलकुलेटर रे के यूज करि छ टेबल सिखियो हला नेक्स्ट क्लास में पचारि भी के सिखिलो और फंक्शन अछि टेबल बोली तुम कैलकुलेटर रे हला तो टेबल ले तुम इजीली एगुडा फाइंड करि परिबो नहले तुमको ईच एंगल पई ए सब जिंस आउथरे टाइप करिया पड़िबो माने कर तुम 1 पई बाहर करलो त ओमेगा रे वैल्यू 1 पई थरे करिवो पुनी डिलीट करि कि नहले बैक एसी दबे कि आउथरे 5 नबो दुईटा रो आउथरे राइट करि कि तो टेबल रे अछि तुमर कोन ए इक्वेशन टा लिखि दबो ऑलरेडी -tan इनवर्स 0.1x देन -tan इनवर्स 0.001x तापर इक्वल टू मारले से आसीबो तमरो स्टार्टिंग पॉइंट तम फ्रीक्वेंसी 1 स्टार्टिंग पॉइंट हला हमरो 1 x रो वैल्यू 1 माने ओमेगा से लिखियो होने कैलकुलेटर रे तो x लिखि पारियो हला तो x रो वैल्यू 1 देन आसीबो एंड पॉइंट तुम दे दो 1000 ओके एंड पॉइंट 1000 तापर आसीबो इंटरवल तो केते इंटरवल रे वैल्यू कैलकुलेट करियो तुम 5 के 10 दे पारियो हला तो 5 10 दे दो इंटरवल ताले से टेबल रे देखे दबो जे x रा वैल्यू 5 पई केते 10 पई केते y पई केते सब वैल्यू आसीबो गुटे संगे रे हला तो तुमको टाइम कंज्यूम होबनी बेसी तो से वैल्यू रा देखि कि तमे पकइबो तो इन दिस केस सेवला बाहर करा है जी एंगल गुरा 50 रु 8000 जाय निया है जी एठी हला तो देखिबो जेंति तमरो -180 को क्रॉस करूथिबार अछि से फ्रीक्वेंसी जाय नबो हला जाहले तुमको -180 जाय क्रॉस करियार अछि तो एटी -180 जाय आसुनी 8000 नेला परे भी त माने बहुत लेट रे आछिबो -180 टा हला तो सिमिलरली ए एंगल गुरा प्लॉट करि पारिबो फॉर 50 फ्रीक्वेंसी वी हैव -81.46 50 टा आसीबो ए पाका पाकी राइट सो -81 ताले ए पाका पाकी पॉइंट आसीबो देन फॉर 100 आसीबो 90 फॉर 100 आसीबो 90 सिमिलरली 200 पे आसीबो 98 200 हेले ए पाका पाकी आसीबो 98 500 पे आसीबो -115.4 500 पाका पाकी आसीबो -1 पर एंगल टा just ignore these angles okay आखिर में लिखे के लिखिया पे मो पेशेंस नहीं एथरे तो एबला ग्राफ टा आसीबो देन we have to the dots तो ग्राफ टा एबले आसीबो to connect the dots so phase plot is easy okay we have to only concentrate on the magnitude plot similarly like this one this will be a phase plot so next we have to comment on the stability of the system
हाँ
so for that क्यों कहू जा okay so next step is to we have to comment on the stability of our system so for that we have to determine the gain crossover frequency and phase crossover frequency so in this we can say up to 8000 we are not intersecting this -180 degree axis right तो जो फ्रीक्वेंसी रे 180 क्रॉस करिवो सेटा हबो हमर फेज क्रॉसओवर फ्रीक्वेंसी तो इन दिस केस वी कैन से द फेज क्रॉसओवर फ्रीक्वेंसी इज इनफाइनाइट राइट वी कैन से द फेज क्रॉसओवर फ्रीक्वेंसी इज इनफाइनाइट similarly the gain crossover frequency the frequency at which it is intersecting this 0 dB axis right so if the frequency is this is about I think 1200 na 1300 आसी होला Electronic phase crossover frequency okay the phase crossover frequency will be around this 1200 or something, right? So the gain crossover frequency will be around this 1200 radian per second, and the phase crossover frequency will be infinite. So we can see here the phase crossover frequency is greater than the gain crossover frequency. So we can say our system is stable. Here, with the phase crossover frequency is greater than the gain. Okay, this is gain. The gain crossover frequency, our system will be stable. So in this case, the phase margin can be calculated. As you know, we have to draw a line from the gain crossover frequency. So this is the 0 dB axis. This is our 0 dB axis. And this is our gain crossover frequency. So from this point, we have to draw a straight line up to this minus 180 degree axis. So now this point, this one will be our phase margin. Okay. So the phase margin is this plus 26 degree. We are getting the phase margin to be 26 degree. So can anyone comment anything about the gain margin? What will be the value of gain margin? Because we are getting the phase crossover frequency at infinite. So what will be the gain crossover? What will be the gain margin?
Sir, infinite.
Yes, it will be infinite, right? The infinite phase crossover frequency margin means gain margin up. So if gain margin infinite means system is stable or unstable?
Stable.
Stable, because we will get positive gain margin, right? We will get positive gain margin because this will be positive gain margin. So it will be a stable system. Clear? So let's come to how we can draw this minus 20 dB per decade, minus 40 dB per decade, and minus 60 dB per decade. Clear? Because this is important. Because you cannot estimate that this will be minus 20 or minus 40 dB per decade line. So first we have to mark that. Okay, so this is our 1 decade. This point is 1 decade. Okay, you can see here in the graph 1 to 10. This 1 to 10 is 1 decade. So this is 20 dB, 40 dB, and 60 dB. Right, linear scale. We have to take linear scale in the y-axis. 20 dB, 40 dB, and 60 dB. So then that point we have to draw a straight line to this point, to this frequency 10, right? We have to draw the straight lines. Straight lines, okay. So that means from positive 20 to, positive 20 dB to it is going this 0 dB. So that means we have a slope of this minus 20 dB per decade. Similarly, this will be minus 40 because from 40 to it is going 0 dB. So it is minus 40 dB per decade. Similarly, 60 dB. So we can draw these straight lines, okay, in the graph paper. And then you can use your set square to draw the parallel line with this one, these things, okay. So that will be very much a tedious work if you use set square to draw this parallel line, right? Because this 20 dB per decade, for this 0 dB it is easy. For this 20 and this 20, we have to draw it parallelly. So this will be a very tedious work. So in my opinion, the simplest method is measure the angle, this angle, okay. For this 20 dB per decade, what is the angle, this angle? So it will be around 19 degree, 18 or 19 degree, okay, this will be. Similarly, measure this angle. So it will be around this 38 or something, 38 degree. You can measure with a protractor, and similarly measure this degree also, okay, up to this one. So it will be around 40 something, 45 or something, I forgot. You just measure with a protractor. So this will be around 18 or 19 degree, okay, for this minus 20 dB per decade. So now you can draw that angle here using a protractor. A straight line, so we have to draw a minus 20 per decade line because you have already measured this angle. So with reference to this line, draw that angle here. Draw this 19 degree point here. Suppose using a protractor, your point is here. So from this point to this point, draw a straight line. Clear? So it will be gone up to the next corner frequency. The next slope is minus 40 dB per decade. So with reference to this line, this minus 40 dB per decade, the angle will be around 38, I think. Okay. So with reference to this line, draw a angle of 38 degree using a protractor. So mark a point on 38 degree and draw a straight line. Clear how to draw this minus 20, minus 40 dB per decade? Or if you invent any other innovative method, just inform me so that in the coming years, if I will teach a control system, then I will tell that to your juniors. I think this is, I find this is very easy, okay, that this angle one. To draw these slopes, minus 20, this minus 40. Okay, let's go to a this type 2 system with a 0. There is a 0 and we have 2 pole at origin and 2 non-zero poles. Okay. So we have to determine the phase crossover frequency, the gain crossover frequency, the phase margin, gain margin, and the stability of the system. So the first step is we have to put this S equal to J omega. And we have to make sure that our transfer function is in the time constant form. Okay. If it is in the pole zero form, then we have to make it in the time constant form. So first we have to put this S equal to J omega. So S will be replaced with J omega. The G of J omega will be this one. So then the next step is to determine the corner frequencies. From these time constants, we have to determine the corner frequency. So we have the time constant are 0.5, 0.125 and 0.1. So we have 3 corner frequencies. So omega 1 is 1 by 0.5, so it is 2 radian per second. And then omega 2 is 1 by 0.125, 8 radian per second. And omega 3 is 10 radian per second. So we have 3 corner frequency. So it is a type 2 system, right? Type 2 system. So what will be the initial slope? Anyone? What will be the initial slope?
minus 40.
Minus 40 dB per
decade. Always tell the unit, okay. Minus 40 dB per decade. And what will be the starting point? Anyone? The starting point and on the y-axis.
सर के रू हमें टाणिबा तो गेन वैल्यू रू हमें टाणिबा से
गेन वैल्यू काढिया केमती काढिया गेन वैल्यू 16 दिया है जी root over of k, right? We have to make omega is equal to root over of k. We have to mark on the x-axis at omega equal to root over of k. So this is our 4 radian per second. So on the 0 dB axis, we have to mark this 4 radian per second. So we have the corner frequencies 2, 8 and 100. So we can start from, so let's start with this graph diagram. We can start with 0.1. Okay, 0.1 will be better. So let's say we have this frequency starting from 0.1. Okay. 0.1, 1, 10 and 100. And we can go up to 1000. So it is a type 2 system. So we have to find that the magnitude plot should start from somewhere on the y-axis. So that can be determined by marking this omega is equal to root over of k. So k is 16. So this is omega is 4 radian per second. So 4 radian per second will be at this point. At this point, right? You don't have to draw the dotted line. Okay. So this will be our 4 radian per second. This point. Okay. So from this point, we have to draw a slope towards this y-axis. So then what will be the initial slope? Because it's a type 2 system, the initial slope will be minus 40 dB per decade. So we have to draw a slope of this minus 40 dB per decade towards this y-axis until it intersects the y-axis. So this is minus 40 dB per decade. Okay, I am not write the dB per decade. So minus 40 dB per decade slope. So now this point is our starting point, because we cannot determine the starting point from this for this system with higher than this type 1 system. Only for type 0 system we can calculate the starting point. Okay, so from this omega equal to 4 at this 0 dB axis, we have to draw a minus 40 dB per decade slope towards the y-axis. So now this will be the intersecting point. So next see this is our initial slope. So let's say see what are our corner frequencies. 2, 8 and 10. So we have to mark 2, 8 and 10. So this is our 2, this will be 8 and this will be 10. Okay. So in this axis it will be 2, 8 and 10. Okay. Corner frequency, this is 2, 8 and 10. You don't have to write in this magnitude plot, okay, because already it is in the this phase plot. To visualize I am writing here only. So this 2. So let's see, this corner frequency 2 is from a pole or a 0. So can anyone say this corner frequency 2 is from pole or 0?
Sir, 0.
0, right. So 0 thile slope कितने होगा?
Plus 20.
Plus 20 dB per decade. तो स्टार्टिंग रे हमर केते अछि? दिस minus 40. ओके, स्टार्टिंग रे अछि हमर minus 40 आ गुटे स्लोप होबो केते 0 कहिना 0 अछि, सो हम ऐड करिबा आ गुटे plus 20 या सहित. Initial slope is minus 40. Okay, then for 0 we have to add plus 20. So now what is the slope? Now minus 20 dB per decade. Right, now this is minus 20. So this will be the slope from this corner frequency 2 will be minus 20 dB per decade. So this slope will be like this one. It will be like, sorry, सीधा ये वाला. Okay, up to the next corner frequency 8. So this is minus 20. Okay, सीधा एटू तुम प्लस 20 dB ड्रॉ करियो नि हला, जहा स्लोप से स्लोप रे हमरा मिसी के आसियो. माइनस 40 थिला 0 पई प्लस 20 एड हला परे नेक्स्ट स्लोप ता हला minus 20 dB पर decade. तो को जाय ड्रॉ करिबा अप टू नेक्स्ट कॉर्नर फ्रीक्वेंसी. तो नेक्स्ट कॉर्नर फ्रीक्वेंसी केते 8. तो नाउ 8 टा कहार कॉर्नर फ्रीक्वेंसी 8
0
जी पोल रो. तो पोल हले ताले केते करी हम आ गुटे ऐड करिवा
minus
केते
20.
प्लस ना minus 20 minus 20. So in this आ गुटे हेबो हमरो minus 20. So now slope केते हला, नेक्स्ट स्लोप केते हबो minus 40 dB per decade.
minus 40.
तो ए पॉइंट रे हम ड्रॉ करिवा आ गुटे minus 40 dB per decade up to the corner frequency 10. Okay, एटा हबो हमरो minus 40. 10 को जीव बोली इंटरसेक्ट करियो माने ना, ऊपर भी रही पारे तळे भी रही पारे. जस्ट इन दिस केस 8 ऊपर कोन 8 को आसीनी, से ऊपर अछि एना से स्लोप टा हबो हमरो minus 20. एई पॉइंट रो हमको 8 को पॉइंट करियार नै हला, हमको स्लोप ड्रॉ करियार अछि अप टू सेही फ्रीक्वेंसी. सेमती minus 40 हला तो तळ को भी आसी पारे 10 तळ को हला. दिस पॉइंट अप टू 10 और minus 40 and the next corner frequency is 10. So 10 कहार फ्रीक्वेंसी पोल रो, राइट. तो पोल मींस हमको आ गुटे ऐड करिया पड़िबो एटी minus 20 dB. So now final slope is minus 60 dB per decade. So 10 रु हम ड्रॉ करिबा minus 60 dB per decade. ए पॉइंट रो सीधा ये लगे ना. ओके, this will be our minus 60 dB per decade slope. एटा को जाय जीवो ए पॉइंट एनी गेस, ए जो एसिम्पटोट हम ड्रॉ करले एटा को जाय जीवो, तेना नेक्स्ट कॉर्नर फ्रीक्वेंसी नाही
सर -180 एक्सिस रे इंटरसेक्ट करिवो
ना किसी करिया दरकार नहीं, यदि करोच भी किसी असुविधा नहीं, जगह हो जदि करोच किसी असुविधा नहीं, करिया दरकार नहीं है। एना फेज प्लॉट और मैग्नीट्यूड प्लॉट दीटा डिफरेंट, तो हमको इंटरसेक्ट करिया दरकार नहीं। तो जदि नेक्स्ट कॉर्नर फ्रिक्वेंसी नथिबो ताहले जस्ट स्लोप टाकले ड्रा करके छाडी दबो हला, तो जो फ्रिक्वेंसी चाहिए जाओ। जदि थिबो कॉर्नर फ्रिक्वेंसी ताहले अप टू सेही पॉइंट ड्रा करिया पड़िबो, यदि नाही ताहले एमती लंबे की छाडी दबो, इंटरसेक्ट करैबोनी फेज प्लॉट को। क्लियर, एटा क्लियर मैग्नीट्यूड प्लॉट एटा डाउट अछि केना फेज प्लॉट इजी हला, जे नै से फेज प्लॉट कर दबो, मैग्नीट्यूड प्लॉट ता बुझियार अछि। तुम निजे एग्जांपल कले जानि होबो ना, माने कोटी ले करूछ तमे, नो प्रॉब्लम है, टाइम नियो करो। तो परे करिवा एग्जाम टाइम रे करिवा कहले हेतो आधा भूल जाइतिबो, एटलीस्ट तुम गोटे प्रॉब्लम सॉल्व करो। मो असाइनमेंट देला बेलू को मॉड्यूल सरला पर मो असाइनमेंट देबी, तो तुम आधा भूल जाइतिबो। ओके, सो फेज प्लॉट ता हमरो ओके क्लियर, केमती ड्रा करिवो -40 dB पर डिकेड -20 पर डिकेड, क्लियर समझते। तो नेक्स्ट है हमारा पेज प्लॉट टा। सो एई केस रे हमरो कोन हबो करेला एंगल टा ना या पे, तो पेज एंगल केते हबो ताहले हमरो गोटे अछि 0 टे। ओके, तो फॉर दैट सो द एंगल ऑफ दिस GH will be division हबो, so it will be tan inverse of ओके 0.5 ओमेगा will be 0.5 ओमेगा, एटा से 0.5 ओमेगा डिवाइडेड बाय 1, तो 1 लिखे दरकार नहीं। तो तापर नेक्स्ट आउट कोन अछि, दीटा पोल अछि राइट, स्क्वायर टर्म दीटा पोल, तो ता माने कोन हला, तमे कोन लिखिया s = j ओमेगा, सो इट विल बी tan इनवर्स ऑफ this omega by 0, then आ गोटे पोल पाई tan इनवर्स ऑफ omega by 0, so 90 हबो, 90 हबो। सो न लिखि के तमे दीटा पोल ओरिजिन थिबो तो सीधा 180 लिखि परिबो हला, आ गोटे पोल थिबो ताहले 90, तो डायरेक्ट 180 लिखि दे परिबो। ओके, रीजन पोल एट ओरिजिन मींस ता एंगल टा हबो 90, तो दीटा पोल अछि।
आउथे रिपीट करिवे सर प्लीज,
हां
सर आउथे रिपीट करिवे एंगल GH पार्ट टा।
अच्छा, तो जे ए को नारो s टा कोन s = 0 + j ओमेगा राइट, केना सिग्मा एथि पई नो ने काहे कि ना हमें एथिरे फ्रीक्वेंसी रिस्पांस करूची, तो सिग्मा रा वैल्यू का हम एठी 0 नो छै, सो 0 + j ओमेगा। तो यार एंगल बाहर कले केते हबो, tan इनवर्स ऑफ इमेजिनरी पार्ट केते ओमेगा डिवाइडेड बाय रियल पार्ट इज 0, तो एंगल केते हो एटा 90 डिग्री राइट। ओमेगा को तुम जते जहा वेरी करो एंगल टा 90 डिग्री हबो, क्लियर। तो यदि गोटे पोल अछि ताहले 90 डिग्री होउची, एंड दीटा पोल थिले कोन हबो, आ गोटे +90 हबो। तो दीटा पोल अछि तमे डायरेक्ट 180 लिखि परिबो, और सिंगल पोल एट ओरिजिन ताहले लिखि परिबो तमे केते 90 डिग्री, तो एटा हे गेला। तो देन नेक्स्ट अछि केते हमरो 1 + j 0.125 ओमेगा। ओके, तो एथिरे कोन हमर इमेजिनरी पार्ट और रियल पार्ट दीटा अछि, रियल पार्ट इज 1 and imaginary part is this 0.125 omega, so it will be tan inverse of 125 omega divided by 1, so no need to write, so divided by 1, and another pole tan inverse of 0.1 omega, clear। सो न्यूमरेटर एटा पॉजिटिव हबो, तो जमन डायरेक्ट लिखिबो जदी tan इनवर्स ऑफ 0.5 ओमेगा माइनस 180 माइनस tan इनवर्स ऑफ 0.125 ओमेगा माइनस tan इनवर्स ऑफ 0.1 ओमेगा, you can directly write। okay, so then we have to vary the value of omega from this 0.1 to our maximum frequency 100। तो एटी केते जे नेछि देखि दो, जो जे 180 को क्रॉस न करूची से जे तमे एंगल टा वेरी करिवो हला। तो ये हमर एंगल वेरी कर 180 क्रॉस कर केते फ्रीक्वेंसी रे फ्रीक्वेंसी 10 रे हमर ऑलरेडी से ताको इंटरसेक्ट करिछि तो 20 30 जाय नै जाय छि तळको हैला तमे 20 जाय नेले भी चलिबो -227.34 तो ड्रा करि पारिबो फेज प्लॉट किछि नै बस ओमेगा रो वैल्यू कंप्यूट करिवो तम कैलकुलेटर रो टेबल फंक्शन रे so let what is the phase margin and gain margin. Okay, so first we have to determine the phase crossover frequency and gain crossover frequency. The phase crossover frequency is calculated at the frequency where this phase plot is intersecting the minus 180 degree axis, right? So this point is the phase crossover frequency. Similarly gain crossover frequency कोटा जो frequency रे मैग्नीट्यूड प्लॉट 0 dB एक्सिस को इंटरसेक्ट करिवो तो सेटा हला हमरो गेन क्रॉसओवर फ्रीक्वेंसी so in this case we can see the phase crossover frequency is less than the gain crossover frequency. That means our system will be unstable. Okay, if the phase crossover frequency is less than gain crossover frequency, then our system will be unstable. Then we can determine the gain margin and phase margin from the graph. The gain margin is calculated at phase crossover frequency. So phase crossover frequency रो single line draw करिवो ऊपर जे है जो जाय कि मैग्नीट्यूड प्लॉट को इंटरसेक्ट करिवो तो we can see ए पॉइंट है राइट ए छोटिया पॉइंट है एती एटा हला केते gain margin is -20 dB पर -2 dB. The gain margin is we are getting -2 dB. and -2 dB ऐड कोले जाय कि हमरो 0 आसीबो गेन मार्जिन रे. ओके so that is why it is negative -2 dB. Similarly এই কোসে फेज मार्जिन टा कोन होची -8 डिग्री काहे ना हम तळो को जाउ छे एपटे एई लाइन रे तळो को जाउ कोन हला हमरो नेगेटिव को जाउ छेला एटा अधिक नेगेटिव को जाउ छी सो फेज मार्जिन इज आल्सो नेगेटिव सो -8 डिग्री. So phase margin is calculated this gain crossover frequency. The gain crossover frequency रे हम लाइन ड्रा करिवा जो जाय कि इंटरसेक्ट करियो हमर phase crossover frequency. तो से पॉइंट हबो हमर एई जो पॉइंट हैला phase margin. तो यहाँ तळ को जाउ छी एपटे सो एटा हला हमर -8 डिग्री. क्लियर. सो phase margin और gain margin नेगेटिव आसिला the system is unstable or we can say the phase crossover frequency is less than the gain crossover frequency. So our system is unstable. Just a minute. हाँ सर हाँ सर मोर क्लास चलछि सर अब 10 मिनिट सरीबो तापर म आपन फोन करि छी. आगे so clear how to calculate this gain crossover frequency, phase crossover frequency, gain margin, phase margin from the body plot.
सर गोटे डाउट थिला
को
सर से गेन मार्जिन और फेज मार्जिन जो एडी अछि -2 dB आ होच -8 डिग्री सेटा मेजर केमति करबा माने
ग्राफ पेपर करियो ना
एक्सेस तो माने बड़ बड़ तार डिफरेंस नोच ना माने 0 ରୁ 10 आउट डिग्री रे होची -180
तमर एटी थिबो ना 10 टा सेक्शन थिबो ना 0 ରୁ 10 नथि जदी और एटलीस्ट तो 5 टा सेक्शन थिबो ना 0 ରୁ 10 भितरे ग्राफ पेपर रे.
हां हां
सेटा तो मेजर करिवो देखो ये 0 ରୁ जो 10 हला केतरा अछि 1 2 3 4 5 हला 5 टा सेक्शन अछि तो सेबला मेजर करिवो एबला रहिबो तमरो सेमिलो ग्राफ पेपर टे हला एटी लिनियर स्केल रहिबो y एक्सिस रे आ x एक्सिस रे रहिबो तमरो लॉगरिथमिक स्केल. तो तमे जदी याकू 10 नैचो कि 5 नौचो से हिसाब रे तमरो हबो फास्ट तमे जो এই পয়েন্টটা বাহার করে দাও হলা যে স্লোপটা ড্র করে কি বাহার করে দাও তো দেখিও সে কেতে ভিতরে আসিবো সেইটা সেই হিসাবে তুমি ড্র করিয়া পড়িও. সো বেটার 28 10 নেলে भी ହେଇଯିବ ହେଲା କିଛି ଅସୁବିଧା ନାହିଁ. हमको स्टार्टिंग पॉइंट से तो एते किछि नहीं होला हमको देखिया जे को पॉइंट से इंटरसेक्ट करिवो.
ओके सर
तो बहुत गुड़ा एग्जांपल अच्छी आ गोटे कॉम्प्लेक्स नंबरटा भी अच्छी सेटा करिया नेक्स्ट क्लास रे काली यदि हमर कॉम्प्लेक्स फैक्टर थिबो स्क्वायर टर्म थिबो सो जदि हमर फेज क्रॉसओवर फ्रीक्वेंसी और गेन क्रॉसओवर फ्रीक्वेंसी सेम हो जाए ताहले कोन हो सिस्टम स्टेबल ना अनस्टेबल एनी गेस
अनस्टेबल
ना स्टेबल हेबा पे हम कोन दरकार फेज क्रॉसओवर फ्रीक्वेंसी टा ग्रेटर देन हेबा कथा गेन क्रॉसओवर फ्रीक्वेंसी यदि सेम हो जाए
सर मार्जिनली
स्टेबल हो हला यदि फेज क्रॉसओवर फ्रीक्वेंसी लेस देन गेन क्रॉसओवर फ्रीक्वेंसी ताहले अनस्टेबल हो यदि समान हे दिया जाको ताहले गेन मार्जिन फेज मार्जिन भी सेम हो एग्जांपल थिला এটা সেম এই জিও গেন মার্জিন ফেজ মার্জিন ওমেগা পিসি ওমেগা জিসি তাহলে সিস্টেমটা হবে মার্জিনালি স্টেবল তাহলে রুটছিলা এই एग्जांपल रे सेम फ्रीक्वेंसी रे मैग्नीट्यूड प्लॉट इंटरसेक्ट करछि 0 dB को और सेम फ्रीक्वेंसी रे फेज प्लॉट टा इंटरसेक्ट करछि -180 को हला सेम फ्रीक्वेंसी सो ए टाइम रे कोन हला हमरो ओमेगा पीसी इज इक्वल टू ओमेगा जीसी सो एट दैट टाइम द फेज मार्जिन गेन मार्जिन विल आल्सो बी सेम द सिस्टम विल बी मार्जिनली स्टेबल फेज मार्जिन गेन मार्जिन 0 so the system is marginally stable right so omega pc omega gc is 100 radian per second so हमको किसी गेन मार्जिन दरकार नहीं फेज मार्जिन दरकार नहीं so at that time system will be marginally stable
सर मार्जिनली स्टेबल माने सॉल्व पे गेन मार्जिन फेज मार्जिन 0 रहेबो
गेन मार्जिन फेज बहुत 0 हे गला माने मार्जिनल स्टेबल सिस्टम रे तो मार्जिनल स्टेबल माने सही पॉइंट रु जदि आमे टिके पछ को जीवा ताल सिस्टम कोन हो हमरो अनस्टेबल हो और जो आकु आसीबा ताल सिस्टम स्टेबल हो सेति पई से जो मार्जिन रे अछि सेति मते तमे मार्जिनली स्टेबल पहुचल यदि पीएम और जीएम +1 हे जाए ताले कोन होबो स्टेबल यदि पीएम जे -1 हे जाए ताले सिस्टम होबो अनस्टेबल सो लेफ्ट ताले केतले 8:30 ना 2 रे सेक्शन ए
सर तीटा
तो ओके आज लैब रे करिया पड़िबो एक्सपेरिमेंट तो 2 टा वाले स्टार्ट करिवो बाय 2 समस्त जॉइन करिवो 11 से सेम लिंक रे थिबो सेम लिंक में जॉइन करिवो मो बाय 150 लिंक टा ओपन करे थिबी सो बाय 2 समस्त जॉइन कर जिवो हला 2 टा स्टार्ट करिया सो मेटा गूगल क्लास में दो जितना एग्जांपल देखि था हला काली आ तो डिस्कस करिया या एग्जांपल अछि हम सिस्टम हैंग गला ओके वेरी गुड तो किछिटा एग्जांपल देखि था हला काली तुम ट्राई करो निज आडू जे जानला पर जानिबो जे कोन तमर प्रॉब्लम रहउची को पॉइंट रे सो हमें डिस्कस करि परिबे हला तो एग्जाम्पल देखिए देता हूँ। So section A will meet at 2 sharp. I will start at sharp 2 o'clock. Okay. So before that, you try to join. So then see you, all of you, section A and B both tomorrow. We will meet again with section A at 2 o'clock.